Okay, assalamu alaikum everyone. So today we are going to talk about the colored image processing, which is part of the computer vision. Since all our surroundings are colored images, we cannot keep talking only about black and white and grayscale images. So we will start talking about the colored images and how the computer perceives colored images. So first of all, we are going to talk about colored images, then we are going to talk about artificial intelligence in 2 different weeks. So we will look at the color fundamentals, the color modes, the pseudo color processing, color image smoothing and sharpening, edge detection, noise in color images, and noise in perception. So the fundamentals of the colors, the Sir Isaac Newton discovered that when a beam of light passes through a glass prism, it will split into different colors based on the wavelength of that color, and the color that the humans and animals most perceives is determined by the nature of the light reflected by that particular object. So if a white color hits a green object, it will reflect the green light, the green color. For example, green objects reflect light when the wavelengths primarily in the range of 500 to 570 nanometers, while absorbs most of the other energies. So the 3 basic quantities that are used to describe the chromatic light source are radiance, which is the total amount of energy that flows from the light source; luminous, which is the amount of energy an observer perceives from the light source, measures in luminance; brightness, which is a subjective, particularly unmeasurable notation that embodies the achromatic notation of intensity of light. So the chromatic light spans the electromagnetic spectrum from approximately 400 to 700 nanometer. Human color vision is achieved through 6 to 7 million cones in each eye. These 3 principal sensing groups are 66% of the cones are sensitive for lead, 33% are sensitive for green, and 2% is sensitive for blue. Absorption of the curves for the different cones have been determined experimentally. Strangely, these do not match the CIE standards for red, green, and blue light, as the standards were developed before the experiments. So the primary colors can be added to produce secondary colors. Mixing the 3 primary colors will give us white. Mixing a secondary color with its opposite primary color produces also white. For example, red plus cyan red. Here is red. Let me change the color. Okay, here is red and here is cyan. If we add cyan plus red, it will give us white. If we add blue plus yellow, it will give us white. If we add green plus magenta, it will give us white. Important differences: the primary colors of light, red, green, and blue. Primary colors of pigments are colorants. So a color that subtracts or absorbs a primary color of light and reflects the other 2. So as you can see here, we have magenta, yellow, and cyan, and if they all intersect, we get the green. We get the black color. So distinguishing one color from another is done through the brightness, which is the achromatic notation of intensity; hue, which is the dominant wavelength in a mixture of light waves, the dominant color perceived by the observer. Example, when we call an object red or orange, we refer to its hue. Saturation is the amount of light mixed with hue. Pure colors are fully saturated. Pink is basically red plus white, is less saturated. Hue and saturation are called chromaticity. Therefore, any color characterized by brightness and chromaticity. The amounts of red, green, and blue needed to form a particular color are called tristimuli values and are denoted by X, Y, and Z. The color is then specified by its trichromatic coefficients, which is x. X is equal to x over x plus y plus z, y is equal to y plus y plus z, and so on. The summation of all three will give us 1, which is white. For any visible wavelength, the tri-stimulus values needed to produce that wavelength are obtained by curves compiled by extensive experimentation. We will return to that point in the last part of our lecture. So specifying colors systematically can be achieved by the chromaticity diagram. On the diagram, the x-axis represents the proportion of red and the y-axis represents the proportion of green used to produce a specific color. The proportion of blue is used in a color is calculated as z is equal to 1 minus x plus y. So this is the chromaticity diagram, and as you can see, the point marked green, which is this point over here, has 52% green, 62% green, 25% red, and blue, which is calculated from this equation. Again, the point marked red over here, which is this point in here. Let me get a lighter color, white. So this point over here, which is point red, is obtained by getting 32% green, 76% red, and 1% blue. Now, okay, so now any color located on the boundary of the chromaticity chart is fully saturated. So these colors on the boundaries are called saturated colors. The point of equal energy, PEE, has equality amount of red, green, and blue, and this point of equality energy, which is this point over here, is the center or the standard pure white. Okay, this is the pure white because it has equal amounts of green, red, and blue. It's almost in the middle. Any straight line joining the 2 points in the diagram is defined as the different colors that can be obtained by combining these two colors. So if I draw a line between blue and green, I will get all the different colors that I can create between blue and green. The same applies between red and green, and the same applies between red and blue. A line drawn from the PEE at any point to the boundary is defined as the shades of a particular color. So from here to here are the shades of red, from here to here are the shades of green, and from here to here are the shades of blue. By combining three given colors, we may obtain the color enclosed in a triangle defined as the three color initials. Now this is the diagram, but now it's without the colors. So here you can see our green, red, here is our green, and here is our blue. A triangle with vertices at the fixed pure colors cannot enclose the entire color region. The triangle shows that the color augment produced by the RGB monitors, the entire color range cannot be displayed based on the three colors. The irregular shapes is the augment achieved by high quality color printers. So this is what you get from the printers, high quality printers. This is what you get from a very good monitor. If you want to go to these outer levels, then you need to pay more money and get better devices. The boundary of the printing gamut is irregular because the printing is a combination of additive and subtractive of color mixing. This is more difficult process to control than the displaying colors on the monitors. Now, in terms of color modes, from the previous discussion, it should be obvious that there are different ways to model color. We have considered two very popular modes used in color processing. We have the RGB and the HSI. RGB is red, green, and blue. The HSI is hue, saturation, and intensity. The RGB modes, each color appears in a primary spectral component of red, green, and blue. The mode is based on the Cartesian coordinate system. So the RGB values are in the three corners, which are the red, green, and blue. In the corner over here is the black, and upper here is the white. And you can see all the combinations. Here we have the cyan, the magenta, and the yellow. And from black to white you have this dotted line, which represents the grayscale colors. Now, images represented in the RGB color consist of three component images, one of each primary color. When fed into the monitor, these images are combined to create the composite color image. The number of bits used to represent each pixel is referred to as the color depth. So a 24-bit image is often referred to as a full colored image, and it has 16,777,216 colors, which is 2 to the power 8 to the power 3. 2 to the power 8 to the power 3. Now, as you can see here, we have the red, we have the green, we have the blue. We give them to a monitor, we get the RGB. Now, generating the RGB image of a cross-sectional colored plane at 127 green and blue. The three hidden surfaces planes in the color are shown in this figure. Now the HSI, on the other hand, which is the hue, saturation, and intensity, the RGB is useful hardware to implement for hardware implementation, and is related way for human visualizing the colors. However, the RGB is not particularly initiative way to in which to describe colors. Rather than people describe the colors, tend to use hue, saturation, and brightness. RGB is great for color generation, but HSI is great for color description. Now, the reminder that hue is a color attribute that describes the pure color, pure yellow, orange, or red. Saturation gives the measure of how much pure color is diluted with white light. And finally, intensity is nearly impossible to measure because it is so subjective. Instead, we use intensity. Brightness is difficult to measure, so instead we used intensity, and intensity is the same as chromatic notation that we have seen in the gray level of the images. So intensity can be extracted from the RGB images. However, human perspective of color does not refer to percentage of RGB. Remember, the diagonal in the RGB color cube we saw previously ran from white to black. Now consider that we want to stand this color, this cube, on the black vertices and position the white directly above it. So this is our black, this is our white, and this dotted line represents the grayscale. The intensity component of any color can be determined by passing a plane perpendicular to the intensity axis. So this is the intensity axis here. If we put a plane perpendicular to the color, we get its intensity. So the intersection of the plane with the intensity axis represents this coloring over here. So you can see, so here you can see that in a similar way we can extract the hue from the RGB cube. Consider the plane defined by the 3 points, which are cyan, black, and white. Cyan, black, and white. All points contained in this plane must have the same hue. Cyan, as black and white cannot contribute in the hue information to a color. By rotating this shape plane around the intensity axis, obtain different hues. So in conclusion, the HSI can be obtained from the RGB values. So to work on these formulas by rotating the shades, in conclusion, we can get these from the geometries. Now, in the middle here, we consider white. Then we have yellow, green, cyan, blue, magenta, and red. If we look straight down at the RGB cube as it was, it was arranged previously, we would see a hexagonal shape with each primary color separated by 120 degrees and the secondary colors by only 60 degrees. So remember, the primary colors are red, green, and blue. So the angle here is 120, the angle here is 120, the angle here is 120. The secondary colors are yellow, cayenne, and magenta, and these are separated by the primary colors by 60 degrees. Okay, so the HSI model is composed of a vertical intensity axis and the loci of the color points that lie on this particular plane in the axis. Now, the hexagonal shape at an arbitrary color point, the hue is determined by the angle from a reference point usually. The saturation is the distance from the hue is determined by the angle from a reference point in the red usually. So this is the hue, reference point is our red. The saturation is the distance from the origin to the point. This is the saturation, which is the distance from here to here. The intensity is determined by how far up the vertical intensity axis this hexagonal plane sits, not apparent in this diagram. So as only an important thing, there are an angle and the length of the saturation vector. This plane is also often represented in a circular or triangular way. So it's different ways, but it's the same idea. Our red is the reference, the hue is the angle, the saturation is the distance, and the intensity is basically the level of how it intersects with the intensity values. So this is how we measure the intensities. As you can see, if we cross section over here, we get the intensity of 0.75. If we cross section over here, we get the intensity of 0.5. Remember, this is our cube, but it is sitting up on its black corner over here. This is another model where we use the circle or the cones. Now, to convert from RGB to HSI, so the hue is equal to the theta is equal to theta if the blue is less than the green, and is equal to 360 minus theta if the blue is greater than the green. S is equal to 1 over 1 minus 3 over the RGB, R plus G plus B, multiplied by the minimum, multiplied by the minimum of the RGB. Theta is the cosine inverse of half R minus G plus R minus B, R minus G square plus R minus B multiplied by I minus G to the power half. And the intensity is equal to 1 over R, G, and B. So given a color has an HSI and its RGB values are calculated as follows. If we want to find the RGB, R is equal to I 1 plus S cosine H, cosine 60 minus H. G is equal to 3 minus I, R plus B. B is equal to I minus S. If, again, H is between 0 and 60 and 190 degrees. In the green-blue section, where H is between greater than 120, less than 100 and 240, we have these equations, and in the last section we have these equations. So what we are referring to, these R, B, and these sections are basically, let me show you here. Here, this is the red and green section, this is the green and blue section, and this is the blue and red section. So this is mainly the idea of how the system or a computer system comprehends the colored images.